Good day. My name is Pavlo Radiuk and I'm a doctoral student from Khmelnytskyi National University. On behalf of my colleague and co-author, Nadiia Hrypynska, who is also a docent from Khmelnytskyi National University, I would like to introduce our work titled A Framework for Exploring and Modeling Neural Architecture Search Methods. Let's begin. The content of the presentation is the following: a brief introduction, problem statement, list of criteria used within the framework, algorithm and framework description, results of the study, and conclusion. So, for the past years, many researchers and engineers have been involved in developing and optimizing deep neural networks. The process of neural architecture design and tuning its hyperparameters remains monotonous, time-consuming, and do not always ensure optimal results. In this regard, the automatic design of machine learning, commonly called AutoML, has been widely utilized, and neural architecture search, called NAS, has been actively developing in recent years. Despite meaningful advances in the field of NAS, the scientific community has not standardized a comprehensive approach to applying search methods. The efficiency of neural models crafted by either manual or automatic search techniques may vary significantly due to the influence of stochastic processes of a particular domain. Despite the simplicity and practicality of quantitative indicators, they do have some significant disadvantages. So, to address these issues, we propose a solution that promotes exploring, comparing, and evaluating search methods both quantitatively and qualitatively. Our approach is dedicated to identifying the strengths and weaknesses of NAS and suggest possible improvements to them. Currently, the most used quantitative metrics to measure NAS methods are training and validation loss, here you can see it to the left, the number of hyperparameters, amount of training data, training and test CPU time, memory requirement, and that's it. More details you can see from our work. Within our framework, we introduce the variance on performance and the level of human intervention as qualitative assessments. To the right of this slide, you can see 5-step evaluation strategy that must be followed successfully. First of all, it's search span design. The goal here is to check the suggested heuristic search procedure for non-standard search placements. Requirements. The purpose of this step is to reduce the likelihood of obtaining suboptimal architecture upon the completion of training. Search process. The goal is to check whether a predefined underlying architecture can be trained in the standard way or whether a specific training strategy should be employed. Adaptation to changes. The aim is to consider in advance the computational cost of any further human interventions. The last but not least, code availability. The goal is to open source a programming code and ensure its reproducibility so that the exploring NAS method can be proved on other machines and datasets. So, in this slide, we introduce the scheme of our network. It consists of 4 stages: setup stage, training stage, adaptation stage, and assessment stage. All these stages are proved by the evaluation criteria block. Next, we will look at each step in more details. So, in the setup stage, we define the search space, here it is, and underlying architecture. The main metrics used in this stage are the amount of training data, memory requirement, search space design, and requirements. On the slide, you can see the typical examples both of search space and underlying architecture. Framing stage. This step is devoted to measuring the computational and memory cost and configuring the architecture search techniques. The criteria employed here are the amount of training data, training and test CPU time, memory requirement, and search process. Adaptation stage. Here we accommodate the various architectural improvements based on the decisions made in the previous step. The metrics utilized here are the number of parameters and adaptation to changes. In the assessment stage, we train and evaluate the sampled architecture. The third and fourth stages form a cycle during which the studied architecture is improved iteratively. So we suggest that researchers should consider the training and validation loss, the number of parameters, training and test CPU time, search process, and code availability as main criteria. When the training finishes, the explored architecture is being evaluated on the validation set. If the found architecture satisfies the initial metrics, the search process stops and the architecture is accepted as an expected result. Otherwise, it is needed to return to the previous step and implement additional improvements to find an architecture that satisfies optimization criteria. Results. Having applied our framework, we discovered some insights. Search spaces are usually represented as hierarchical structures. Set of handcrafted recognized networks remains the popular type of underlying architecture. Bifurcated and cascaded search strategies are widely prevalent among the manual nest methods. In contrast, automatic search methods are mostly based on reinforcement and evolutionary strategies. The primary goal of most search methods remains task error reduction. Individual building blocks and diverse levels are commonly utilized in the adaptation stage. Among sampling techniques, pathfinding and parameter sharing are in favor. The number of works with open source code is approximately equal to the number of work without code. So, conclusion. To sum up, we propose a new framework for exploring and modeling new search techniques. The qualitative evaluation side of our approach is based on the standard metrics that measure both individual architectures and search methods. Within our framework, we introduced 5 qualitative assessments to ensure the variance of performance and the level of human intervention. Our work describes all the critical aspects of state-of-the-art search methods and summarizes search insights. The proposed framework imparts a better understanding of recent and noticeable contributions made in the development of neural architecture search. That is all. Thank you for your attention. Goodbye.